If you found yourself in the world of linear algebra, then you may have come across this formula for projection matrices. Or maybe you're in the world of statistics and have seen this related formula when performing linear regression with ordinary least squares. If you found these expressions perplexing, then you're not alone. It's very common for these to feel like a gibberish of matrix algebra at first. But our goal today will be to make sense of these formulas. It turns out that they both fall out from doing orthogonal projection, which is when you take a vector and essentially cast a shadow onto some subspace of interest. This video is going to explain things generically in terms of orthogonal projection first, and then at the end, as a treat, we'll tie it back to linear regression. This is actually the second video in a series on projection in linear algebra, and in the first video we explored the properties of projection matrices. Of course, I won't object if you go give it a watch, but you shouldn't need to in order to understand this video. The basics of orthogonal projection begin with the dot product. The dot product of two vectors is defined as what you get if you multiply the lengths of each vector by the cosine of the angle between them. It also turns out to be the case that you can calculate the dot product by multiplying the corresponding components of the two vectors and then adding them up. It's rightfully a bit mysterious that these two procedures should give you the same number, but you can find proofs of this elsewhere, and we'll just take it for granted. Now cut to projection. We'll suppose we have two vectors, call them x and v. We'll also suppose that we know the components of x and v, which we could use to figure out their lengths and their dot product. Our goal is going to be to project v onto x. When we do that, we're looking for a new vector, call it p, which essentially is the shadow of v in the direction of x. This is the projection. Because the projection points in the same direction as x, we can write an equation for it as a multiple of x. Note that p and x are vectors, but p sub x here is a scalar, just a number. We can also consider this other vector that should be the difference between the projection and our original vector, which would be v minus p. This sometimes gets called the rejection vector. Because we're doing orthogonal projection, this rejection vector will be perpendicular to the line we're projecting onto. Actually, you can think of v minus p as itself being a projection of v onto this line over here. But I'm going to sidestep that for this video. Anyway, using v minus p, we're now drawing this right triangle. What we actually want to know here are the components of p, but knowing that the rejection is orthogonal to our projection line is going to be very useful for us. Whenever two vectors are perpendicular, their dot product must be 0, because cosine of 90 degrees is 0. So, we can express this fact as an equation, that x dot v minus p equals 0. The dot product distributes over vector addition, so we can do some rearranging here. Now we can substitute our equation for p into this. We can solve for p sub x to get it by itself, which gives us this expression. In that denominator, any vector dotted with itself gives its own length squared. For our first and simplest case, we are going to suppose that x is a unit vector, so its length is just 1. In that case, the denominator of this expression is just going to be 1. So this reads that the component of the projection in the x direction is given by x dot v. To get the full equation for the projection, we can plug this back into our expression for p. This is the thrust of the math, and hopefully it's been mostly straightforward so far. The next step is just to gussy it up a bit by dressing it up in matrix algebra. If we represent these vectors as column vectors, then one fact we need to know is that we can get the dot product by taking the transpose of the first vector, matrix multiplied by the second vector, like this. So the component of the projection along x becomes P sub x equals x transpose matrix multiplied by V. And the full vector P equals x transpose times V times x. X transpose times V is just a number, so we are free to rearrange this equation a bit into P equals x transpose V. This is cool because it's giving us our first projection matrix as x transpose. A projection matrix is a matrix that you can multiply a vector by to get the projection of that vector. In this case, if we want to project some vector v, we can multiply it by the matrix given by x transpose. If the dot product is sometimes called the inner product, this form is sometimes called the outer product. The result is a rank 1 matrix that, if you multiply it by v, gives you the projection of v along x. And just what does this matrix look like? It's definitely got an oddly satisfying kind of aesthetic to it. The components of the matrix are every pairwise product among the components of x. You can also see right away that this matrix is symmetric, since all the off-diagonal elements just have the same products on them, and that's good because we know from the previous video that orthogonal projection matrices have to be symmetric. Where we should go next is to ask, what do we do if x is not a unit vector, if it has some length other than 1? This is not going to change the vector p at all, but it will change our representation of p as a multiple of x. Let's back up to this equation here. If x isn't a unit vector anymore, then the denominator is not going to reduce to 1, so we'll have to leave it as is. This term is what we would call a normalizing factor. What it does is take account of the fact that our x vector isn't unit length, and so corrects for that. By the way, why is it squared? It's because of what happens in the full expression for p, which we can again get by substitution. Notice that the length of x shows up once in the dot product in the numerator, and then again because of the x on the right. We need to cancel both of those, hence the second power in the denominator. Anyway, let me rewrite this with the dot product, and we get the full expression for our projected vector as x dot v divided by x dot x all times x. Now let's go to matrix notation. Starting with the component, just p sub x, the numerator converts the same as before into x transpose v. The denominator will become x transpose x, which I'm going to pull out into its own term. When we plug this component into the full equation for p, we initially get this form, but then we can do the same trick we did earlier to rearrange the last three terms to get this expression for our projected vector. Okay, and if you digest what's going on here a bit, this is very similar to our previous case. We can write our projection matrix now as x transpose divided by x transpose x, again a pleasing bit of symmetry. The x transpose part is the outer product, while the x transpose x is the inner product, which deals with normalizing for the length of x. For those keeping score, although you can't divide by a matrix, that term in the denominator is just a number, so we can do that division. Just to foreshadow mysteriously what's coming soon, I'll leave this by rearranging one more time to put the x out in front. Okay, that's all projecting a one-dimensional vector onto another one-dimensional vector. What if we want to project onto other things, higher dimensional surfaces? Like what if we want to project a vector onto a plane? Or maybe project a vector onto, well, higher dimensional things that seem hard for us to visualize, but still conceptually seem like they should be possible. Well, we can do that. We'll start from the simplest case first, then generalize. We're going to project this vector v onto this plane here. We'll need two basis vectors to span this plane, and we'll call them x and y. These will essentially form the coordinate system for our plane. We'll again suppose that we know the components of all three of these vectors, and therefore we can find the lengths and angles between them too. The projection of v, which we can again call p, is going to lie somewhere in this plane, and unlike before, that may not be perfectly in line with either x or y. What we can do, though, is express p as a linear combination of x and y. What we're looking for, then, are components along those basis directions, and then these add up to give us the full projection p. As an equation, we can write p as a sum of these components. We'll again also consider this vector here, which we get by taking our original vector v and subtracting the projection p. This vector, v minus p, is again called the rejection vector, and it is orthogonal to p. Actually, not just that, it's going to be orthogonal to the plane in general. And if v minus p is perpendicular to the plane, then it's also going to be perpendicular to every vector in the plane, including x and y. So we can get two equations by taking the dot product of this vector with x and the dot product of this vector with y and setting them both to 0 to represent that they should be perpendicular. Simplifying, we get these, and then substituting in for p gives these. In the simplest case, we'll suppose that x and y are orthonormal, which means they are both unit length and also perpendicular to each other. Why does this come out to be the easiest? Because if x and y are perpendicular to each other, then the components of p along x and y are both going to be projections. We can project v separately onto x and onto y, then just add those up. And we've already seen that if the vector you are projecting onto is a unit vector, then the projection is especially easy. Okay, so x and y are orthonormal. What the ortho or orthogonal part of that is going to do for us is that it allows us to cancel the cross terms. When we dot x with y, those are perpendicular, so we get 0. That brings the equations down to this. Then what the normal part does for us is that if x and y are each length 1, then the vectors dot themselves also gives 1. The equation's reduced to just this. And that's news we can use. That tells us the components of the projection p in terms of the plane basis vectors x and y. It tells us that p has this form. Each term here is exactly what we saw in our very first case, and so it really is like we are projecting separately onto x and then y and then adding them up. And we know from before how projection matrices go, at least for each term separately. Now we can factor out the v to get the overall projection matrix as x transpose plus y transpose. This builds nicely on our earlier work, showing that our new projection matrix is just the sum of separate projections in the x and y direction. But let's go one step further. This expression is easy to write in matrix form, like this. Remember, x and y are column vectors, so this first matrix has 2 columns, and the second matrix transposes them to get 2 rows. Let's give the first matrix the name A, but don't get confused. A is just a matrix that puts x on the first column and y on the second column. Using this definition for A, we can write the overall vector p like this, as A transpose v, and we can write the components for p as A transpose times v. So our projection matrix is A transpose, which again looks like an outer product, which is turning out to be a recurring theme. We can also compare this to our earlier expression to reason that this projection matrix is actually the sum of the outer products of each of our basis vectors. Okay, so that was the case of orthonormal basis vectors in the plane. Next, consider when x and y are still orthogonal, but now we'll relax the requirement that they have length 1. And so we'll consider what happens if x and y have different lengths. Maybe for this example, we'll lengthen x, and maybe we'll shorten y. Looking back at the formulas for our components, if the lengths of the basis vectors aren't 1, then the denominator isn't going to vanish. Let's substitute this back in to get our projected vector, and then we can rewrite all of that in matrix form and rearrange a little. What we get is pretty similar to what we saw before. It's a sum of two outer products, two lower dimensional projection matrices, to get a higher dimensional projection matrix. However, it also has these scaling factors that deal with the lengths of these vectors, and those scaling factors are about dividing by the inner products. It turns out that, using the same A matrix as before, which puts x on a column and y on a column, there's a relatively tidy way to write this expression. The full projected vector comes out like this. P equals A transpose A inverse A transpose V. The components of P come out like this, just missing the factor of A in front. You can brute force through the steps and see that it comes out right, but we'll give a simpler explanation for why these formulas look this way in just a moment. For now though, the outer terms of this formula, the bread, if you were to think of it as a sandwich, is the same A transpose outer product which we saw before. The filling of the sandwich, this inverse inner product, is exactly the term we need to be the scaling factor, which deals with the vectors not being length 1. Okay, so for our next case, we want full generality. We've been considering our x and y basis vectors to be at 90 degrees, but now we'll let them point in any crazy direction, like maybe these here, and we'll let them have any length. We do still need the basis vectors to span the plane, so they can't be right on top of each other or outside the surface, but otherwise anything goes. Although the projected vector p is still going to be the same, its components in terms of the basis vectors will be more complicated now. If there's a non-90 degree angle, then the components that would add up to p are not going to simply be orthogonal projections anymore. But we can still find them using the same method. We'll consider the rejection vector v minus p, which is still perpendicular to both x and y, so we can write out our two normal equations. And we can still break our projected vector down as a sum of components along x and y, and substituting that in gives this. Distributing the product gives us the full equations again, but this time, unfortunately, nothing is going to cancel. So what we have here is a system of two linear equations with two unknowns, which are the components of P. Fortunately, there's a standard linear algebra approach for dealing with these. Collect the terms into matrices, then solve. You may want to pause the video and make sure you followed that step. As some fun terminology, the matrix of dot products between our basis vectors gets called the gram matrix, and in tensor calculus, it's closely related to the idea of the metric tensor. But anyway, what matters for us here is that we can solve this equation by inverting this matrix. Before we do that though, let's translate these dot products back into the language of matrix multiplication. Then we can do some factoring, which gives this. This might be another good spot to pause the video to make sure you followed that step. And now using our matrix A, that once again has x on one column and y on the other, we can condense some more. Then we invert the term on the far left to solve for our projection components. And finally, we'll plug these back in to get our projected vector. Start with the formula for the projection and factor it into matrix form. Notice that the first term is just A, then substitute in our components. This looks familiar from earlier. The A transpose A inverse term in the middle is our normalizing term, dealing with the fact that our basis vectors x and y are not orthonormal. Then the outer terms A and A transpose form our outer product. And that whole big term, A transpose A inverse A transpose, is our projection matrix. We could now do this game in higher dimensions, projecting onto hyperplanes instead of just planes, but we don't need to walk through it again because everything works out exactly the same. So voila! There we have it. This is where the formulas for projection matrices come from. Okay, on to the final section of the video. As promised, as your treat for making it this far, let's tie this back to linear regression in a statistics context. Linear regression is often framed as being about finding a line that best fits through our data points on a scatter plot. And that's fine and all, but the projection approach gives us another way to think about what's happening. To keep things tractable, let's consider fitting a line through just 3 data points. Behind the scenes in regression, we're actually writing a separate equation for each one of the data points. And so with 3 data points, we can write that as 3 equations, like this. Here, the beta 0 is the vertical intercept of our line, and the beta 1 is the slope, and you'll notice that these same values are shared between each of these equations, only the data points change, the x and y values. Hopefully your danger detector is already going off here, because we have 3 equations but only 2 unknowns, beta 0 and beta 1. That means there might not be any solution to this system, meaning no values for the betas that can make all of these equations true at the same time. Or in other words, there might not be any single line that can pass through all 3 of our data points. But that's okay, because that's what projection can help us with. Let's collect these equations into vectors. And then represent these as arrows in 3D. We'll have one vector for y, and a vector for x, and a vector of 1s. This may be a little bit different from how you're used to representing the data, but it's a perfectly good alternative picture. Next, let's consider the plane that is spanned by our x vector and the vector of 1s. This plane contains all the vectors that we could get by taking linear combinations of the 1s and the x vector. Basically, it shows what the results would be from choosing all possible values for the betas. Now, if our system of equations had a solution, then what we would see would be that the y vector would lie somewhere in that plane. Again, that would correspond to the case where all 3 of our data points happen to lie on the same line, and there would be a unique choice of betas that gets us to y, which we'd represent as the vector sum of these components. But what if the y vector lies outside the plane? Then what can we do? The strategy of least squares says, let's project y down onto our plane, and we can call that y hat, then choose beta values which can get us to that projection. In other words, the betas are the components of the projection. Students often wonder, why is it called least squares? Well, we don't have to do orthogonal projection. We could pick any other vector inside this plane, and it would still count as a linear model. But you can figure, if our model is good, then the prediction it makes for y, which is what this y hat vector is, should be as close as possible to the actual y vector from the data. So which choice of y hat comes as close as possible to the actual y? With a little bit of reasoning, you can convince yourself that it must be where the rejection vector, y minus y hat, is perpendicular to the plane. Any other choices for y hat are going to be farther away. Only the orthogonal projection is going to minimize this distance, and minimizing this rejection vector is exactly why it's called least squares. You can show that this whole process will minimize the squared length of this rejection vector. The loss function that we use for OLS, the sum of squared residuals, is just the squared length of this rejection vector. Anyway, to get the formula, we can repeat all the same routine we've done a few times now. Since these are orthogonal, the dot product of the projection and the rejection gives 0, and, speeding through it a little bit faster than before, if we stuff our basis vectors into a matrix that we'll call bold X, we can get to the standard formulas for least squares regression. Alright, that was a lot, so let's end this chapter here. Hopefully this video has given you some better insight into where the formulas for orthogonal projection and least squares come from. In the next video, we'll consider what happens when we don't project 90 degrees anymore, and instead project at some other angle, which is called oblique projection. Hopefully I'll see you there, and thanks for watching.